Okay, today we're going to be looking at logarithmic functions and semi-log plots. So that's topics 2.11 to 2.15. Okay, so 2.11 is going to be log functions, 2.12 log manipulation, so shifting it left, right, up, down, and looking at how our graphs work with them. And then 2.13 is equations, 2.14 is context and modeling, and 2.15 is semi-log plots. Okay, so let's look at 2.11 first. So for the general form that logs are going to be in, it's going to be A, which is going to be our vertical shift, log B, which is just our base, X minus H, which is if H is positive, then it's how much we're shifting our X to the right, and if it's negative, then it's to the left. And then plus K, which is up or down. And B cannot equal 1. And X minus H cannot equal 0. So that's going to be the general form that logs are going to be in. And our parent graph is going to be log, and then there's no base, just b of x, so it's base 10. So, and the domain for a parent log function is x. It's all values where x is greater than 0, because if you think about it, any base to the power of something cannot equal a negative number unless the base is negative, but we don't work with negative bases in log functions. And also the x-intercept will be at 1 comma 0, and that's because any base to the power of 0, which is the y, would equal 1. So that's why that is. And we're going to have a vertical asymptote at x equals 0, because we know that b of x, where bx, anything, let's say b is like b equals 2, any number like of a y value, 2 to the power of y equals x, right? Well, anything, no matter what number y is, x can never be 0, so therefore there's a vertical asymptote at x equals 0 from parent graph. And for the transformations, it's the same rules as other functions like quadratics and linear functions. H shifts right, k shifts up, and a stretches vertically. When b is greater than 1, we're increasing and concave down. So it would be like that. When b is between 0 and 1, we're going to be decreasing and concave up. So it would be like that, which is that depends on our b value. So like log b x equals y, and it depends on the b value. This is when b is from 0 to 1. And there's no extremal or inflection points on log functions. It's always either concave down or always concave up. Here, let's look at this log plot. First thing, let's find our x-intercept. So our x-intercept is going to be obviously when x is 0. So let's put that in. So x equals 0. Well, actually, if you look at it, x equals 0, then it would equal -2. This part right here. And it would become log 2, -2 plus 1. And we know that no number, it can be put to an exponent. That's no number that's positive can be put to an exponent and turn negative. So therefore, there's no point for this. And this, like this is our h value. So it actually gets shifted right 2 units, which means our x-intercept, which is, our first point, which we always have a point. It mentioned that we always have a x-intercept at 1 comma 0. That's going to be shifted right twice. So that's going to become by 2 units. So that's become 3 comma 0. And this is our k value, right? So the 3 comma 0 becomes 3 comma 1 because we're adding 1 as well. Okay, so it's going right to up 1. And that's for my h and k values. So we just have this point right here, which is going to be 3 comma 1. And our vertical asymptote, it's normally at x equals 0, right? But since we're shifting the whole graph right 2 units, we're going to have a vertical asymptote at x equals 2. So that's why there's the vertical asymptote here. So here's an example. Okay, the things I'm seeing. Vertical reflection. This is right VR. And then the 3 is our A value, so stretch by 3. And then here, x plus 1, this is our h value, and it seems to be negative, so we're doing left 1, 1. And this is down 2. I'm going to write D2. So now we know all the things that are happening to this graph. So as you can see here, reflected plus stretched by 3, stretch 3, left 1, correct, and down 2. And this graph is, it would have been concave down because the B value, which is 5, B equals 5. Since B is greater than 1, this would have been concave down. Except the thing is that since we're being reflected by a vertical reflection, this actually changes to being concave up, CU on the right. So when you're being reflected, it changes concavity to on log functions when the graph is being reflected vertically. Here, we're writing limit statements for this. So we know that we have a vertical asymptote at x equals 0 since it's not being shifted. So VA at x equals 0. And as x approaches, remember this means plus means it's coming from the positive side, so from the right, g of x is going to go to negative infinity. So let's say our graph is like this, and this is going to be our vertical asymptote, right? At x equals 0. Obviously, from the left, there's nothing. There's just no graph, right? So like this place, it's all just empty. But from the right side, you can see that it's approaching negative infinity. And it'll keep going. And remember that our x-intercept is going to be 1 comma 0, since this is basically just your parent graph. So 1 comma 0. And then as x approaches infinity, this keeps going toward infinity. Even though it starts like decreasing at the rate at which it goes to infinity because it's concave down, it still is approaching infinity. So the graph is increasing and concave down. And our end behavior is going to be limit x approaching 0 from the right, g of x equals negative infinity. And then we have as x approaches infinity from as x just approaches positive infinity, g of x also approaches positive infinity. I'm not gonna write that one out since we've already worked with limit statements a good bit. All right, now I have 2 problems for you guys. So for the first one, find the vertical asymptote, domain, range, x-intercept, and describe increasing, decreasing, and concavity of this graph. And to do this, first analyze your parent graph. So parent, remember that the domain of the parent is going to be x is greater than 0. It's our domain. And the range is all real numbers. By the way, this is another way you can write all real numbers. It's kind of like an R with 2 lines going through it. And then now just look at what these values are doing it to it. So what's your A value doing? What's this value doing? What's this value doing? And with that, you can find your domain, range, vertical asymptote, and x-intercept, and increasing, decreasing concavity. And then for problem two, describe the transformations that produce g from the parent log. So what's that saying is your original log function would be log, we keep the base, so log to x, and that's it. It's asking what transformations were done to this graph of log 2x to get this graph of negative log 2 x to x plus 3 plus 5. And give the end behavior and limits as well. Okay, I'll give you guys a couple minutes to do that and then solve it right after. All right, I'm gonna go ahead and solve these two questions in 3, 2, 1. Okay, so for the first question, we have to look at the properties of our parent function, which is just log 3x in this scenario. Our x-intercept, okay, let's look at all of them. Our vertical asymptote would be, right now I'm mentioning all the things of the parent function only, right? Vertical asymptote is x equals 0. Domain, we already said, is x greater than 0. Range is all real numbers. The x-intercept is x-intercept is 1 comma 0, remember. And then on our usual function, it would be increasing. Increasing, and concave down. Okay, now let's look at what's happening to our graph. Okay, first of all, I see no reflection and nothing like happening to where like our concavity or increasing, decreasing is changing. So this can remain that the graph is increasing and concave down, down. And then our vertical asymptote, but we do see a horizontal shift. So our H value is going to be equal to 4, right? So that means we're shifting our thing right 4 units, which means our vertical asymptote also shifts. So vertical asymptote is now x equals 4. So that's been shifted, okay? That means our domain also has to shift from x greater than 0 to x is greater than 4. Now, if we look at our range, it's all real numbers. And again, that just stays all real numbers. So that stays the same. Range is going to stay all real numbers. Now, the last thing we have to look at is our x-intercept. Okay, we see our h value is 4, which means it's shifting right 4 units. So R4, and it's plus 1. This is our k value. So plus 1 means it's going up 1 unit. So up 1, U1. And we know our original x-intercept is 1 comma 0. So if we shift that 4 units, that's going to be 5 comma 0. But we can't forget that we also need to move up 1 unit. So it actually becomes 5 comma 1, which equals our x-intercept. And from that, we got the 5 values they asked for just from looking at the transformations on the graph, which they've given us from the graph. And it's pretty simple, right? You just have to identify the properties of the parent graph. And then from there, you can just shift them over and you get your answers for these type of questions. Okay. Now describe the transformations that are producing from G from the parent log. The parent log is just log base 2 x, right? So what's happening to G? First of all, I see there's a negative sign in the front. So that means it's a vertical reflection. So I'm going to write VR. All right, next, x plus 3. This is an h value of negative 3, right? Because normally it's in the form of h minus, no, sorry, x minus h. And since this is plus 3, that means it must be h minus negative 3, which would just equal h plus 3. So it's going left 3 units. And then finally, looking at our k value, it's going up 5 units. So there we go. We've got the properties, the transformations that happen to this graph. Now, end behavior limits. So our parent graph, first we have to find the end behaviors of our parent graph and see what's happening to it. So our parent graph, end behaviors is going to be limit here. We can do this over here. The parent graph of just log 2x end behavior, I'm going to write right here. So the first, we have limit x approaching 0 from the right side, which is indicated by a plus, g of x equals negative infinity, and then limit x approaching negative, so infinity, g of x also equals infinity. And we know this because our graph is going to look something like this, where this is the asymptote. Now, since we're shifting it left 3, up 5 actually doesn't change anything, but left 3 does, and there's a vertical reflection, which does as well. So first of all, left 3 shifts our asymptote by 3 units. So it goes to left 3 units. So our new graph is going to look something like this. So our asymptote is actually going to be, instead of x equals 0, it's going to be x equals negative 3. And then that means, and we can't forget there's a vertical reflection as well. So this is going to, instead of normally, here, I'm going to draw with the red, our normal graph. Our normal graph was going like that, right? Parent. But our new graph, it's going to be a vertical reflection, and it's going from negative 3. So it's going to go something like that. And forgot to label the asymptote for our parent graph. That's our asymptote. So looking at this new graph we have, we can see that it's not limit when x approaches 0, but rather limit when x approaches negative 3 from the right side. G of x actually equals infinity, not negative infinity. And limit, so let me write that. And then for our second one, limit g of x, we can see that it keeps decreasing to negative infinity, so equals negative infinity. Sorry about that, scraping into that other side. When x is approaching infinity, because as you can see, it's approaching infinity, and this just keeps going down. Approaches negative 3, and it just goes up. And therefore, we've got our 2 end behavior limits for this equation from that. Okay, now 2.12, properties of logs. So the first property is the product property, which means if we have 2 logs of the same base, for example, log 2 of 3, and then plus log 2 of, let's go with, it's a good number to do for this. Just do log 2 of, or we'll just keep it simple, log 2 of 4, right? This equals log 2 of 12. So when you're adding 2 logs, it equals and they're both of the same base, you can keep the base the same and multiply the arguments. The arguments are what's over here. The 3 and the 4 are arguments. I'm just going to ARG. Arguments, they can multiply together to equal log b of xy, which is 3 times 4, instead of log b of 3 plus log b of 4. So, by the way, these properties, you guys have to remember to like solve log equations, and you'll have to do this on your AP exam and like a bunch of places. So just make sure to remember these. And I'm pretty sure you guys learned this earlier in algebra 2 as well. So there's that, but it's good to refresh on these. So log b of x over y equals log b of x minus log b of y. So if this was log b of 7 minus log 2 of 7 minus log 2 of 3, then that would equal log 2 of 7 over 3. If we have log b of x to the n, so for example, log b of 4 cubed, this equals log 2 of 4, and then we move the 3 in the front. So log 2 of 4, we know that 2 to the power of 2 equals 4, so, and 3 times, and so therefore log 2 of 4 equals 2, then 3 times 2 equals 6. Does that, and we can check that over here. 4 cubed is 64, and 2 to the power of 6 is also 64, so that works. Change of base. So if we have a log of like log b of x, then we can take both the base and the argument and put a natural log or just a normal log function in front of it and make it like the argument over the base. So these are like horizontal dilate. You don't really need to know this part much. But here, for example, log 2 of 8x cubed. Remember that 8x, and they're asking you to expand this, right? 8 is just 2 cubed. So basically 2 cubed x cubed. So it's basically saying 2x cubed, right? So that then it becomes log 3 log 2 of 2x. And since it's 2 times x, you can split that into 3 log 2 of 2 plus 3 log 2 of x. And 3 log 2 of 2 is just 3. So it becomes 3 plus log 2 of x. And then condensing here, instead of it's since the 2 is in front of this is the same as ln x squared, right? So, and then since we're subtracting, it would be ln x squared divided by y. So x squared over y. It's a division. Sum slash difference of logs. Again, we're just separating the squares and like all that stuff. So we see that x squared, so we move the exponent in front, log 3 of x, and we're multiplying by square root of y. And remember, square root is the same as putting to the power of 1/2. So we're going to do 1/2 log 3y. And then finally, we're going to subtract log 3z because z is on the bottom. It has no exponent, so it's just log 3z. Here, evaluate without a calculator. Okay, so we have log 5 of, okay. Honestly, I don't know what they want you to do here. I wouldn't expect you guys to evaluate this without a calculator. Yeah, you can split it into ln 40. Oh, it says with the calculator. Oh, I see. Well, yeah, then actually this is still kind of pointless because I mean, like then you would just evaluate log 5 of 40. But yeah, this splits up into ln 40 over ln 5. So there's still that, I guess. But yeah, there you go. And you get 2.292 if you plug that in. Okay, now 2 quick problems. I'd estimate like 2 minutes, 3 minutes for you guys to do these two, and then we'll move on to the next problems. So I'll give you guys that time now. Yeah, I'll solve it right after. I'm gonna go ahead and solve these questions in 3, 2, 1. Okay, first question. First, we know that terms that multiply together by our property of our product property, log A plus log B equals log AB. And then in a similar way, log A minus log B equals log A over B. And then we have our exponential property, which moves the thing to the front. So first of all, log 4 of 16, that just equals 2, right? And we know that we're doing log 4 of 16 plus log 4 of x cubed. So we can just put 2 there, and 2 plus log 4 of x cubed, except we know that with exponents, we can move the exponent to the front. So log 3 log 4 of x. And since y is on the bottom, we have to subtract by log 4 y squared. And again, we move the exponent to the front, so it becomes 2 log 4 y. And that's going to be a fully expanded thing. Now condense into a single log, 3 log x plus 1/2 log y minus 2 log z. Oh yeah, we know that when we're adding, we multiply them, so it's going to become log of, on the top, we have x cubed times square root of y, since y to the 1/2 is the same as square root of y. And then we're subtracting by 2 log z. Again, we move the exponent on top of the z, so 2 log z is the same as z squared. So we have z squared. This is going to be our entire equation condensed into one log. Now, for these two questions, change of base. So log, we know that our change of base property is just log a b equals, it equals ln a over ln b, or even log a and log b, as long as the two log functions have the same base. It doesn't matter which base you use, but it has to be the same base. So this would equal ln, no, sorry, by the way, swap the b and a here. So this would be b a b a. I swapped those around on accident. Okay, so here would be ln 200 over ln 7. That's our answer. I have a calculator on me, so I'm just going to leave it at that. But you guys could solve it with the calculator. Then we have ln 0.5 over ln 3. And just like that, we've got our two answers. And no calculator, so we're not going to evaluate them, but those are our two answers in the form of logs. Now, exponent and log functions. So it's basically just teaching us how to solve for exponential functions using logs. So for example, if 2 to the x equals 10, then we take the log to make it x, which is what the power is, right? X log 2 to the 10, and x equals log 2 to the 10. So this would just be our answer for x, but we could also put this in the form of, using the change of base, we could put it as ln 2 10 over ln 2. So it's pretty cool, just like that. And that equals approximately 3.32 using our calculator. And here's another example, converting to exponential form. We put the bottom, so 3 to the power of the answer, 4 equals x, which means that x equals 81. Also, tip, check for extraneous solutions. Log arguments must be positive. So for example, if you got like 2 to x equals something, and you end up getting something where the answer is negative or 0, can't be the answer. So that's extraneous. And when you condense logs to solve, plugging the answer back could give a negative log, and that's going to be extraneous as well. Like I just mentioned, they have to be positive. So yeah. Here, let's solve for this. 3 to the 2x, 5 times 3 to 2x equals 405. First thing we can do here is just divide by 5, which is going to be 81 if I'm not wrong. So that's going to be equal to 3 to the 2x. And since 3 to the 2x equals 81, excuse me, we use our log property to where it becomes log 3 of 81 equals 2x. And we know that log 3 of 81 It's just 4. 3 to the 4 equals 81. So 4 equals 2x. So x equals 2. So our answer for x is going to be 2. We just solved that pretty easily with logs, right? Here, log 2 of x plus log 2 of x minus 2 equals 3. Let's solve for x. So this is the same as log 2. Remember, adding them is the same as uh, adding two separate log functions is the same as if they have the same base, then it's the same as multiplying the arguments. So x times x minus 2 equals 3. And now we just know that 2 to the power of 3 equals x times x minus 2. So 2 to the power of 3 is 8. So 8 equals x squared minus 2x. Now we just turn this into a quadratic, right, to solve for x, which becomes x squared minus 2x minus 8. And with our factoring skills, we can just work that out to be x minus 4, x plus 2. So our answers would be, okay, I don't know what just happened there. Okay, they are, what? It's weird. Okay, here's the back. Okay, x minus 4 times x plus 2. So our answers would be x equals 4 and negative 2. Except, remember, we have to check for extraneous solutions. If we plug in negative 2 to our original equation of x, then that's going to result in a negative argument. And we know that x has to be greater than at least 2, because if x equaled 2, for example, then x minus 2 equals 0, and the argument would be 0. So x equals 4 is the only valid answer. So x equals 4 is our answer. Now I have 2 questions for you guys to work on. Solve each equation. 4 to the x minus 1 equals 64. E to the 2x equals 15. And for problem 2, check for extraneous solutions and solve. And yeah, then I'll give you guys I think you guys can do this in like 4 minutes, and then I'll go on to the next problem and first explain it to you guys, of course. Okay, I'm gonna go ahead and solve these questions in 3, 2, 1. Okay, so we have 4 to the x minus 1 equals 64. First, let's take the log. So log 4 of 64 equals x minus 1. We know that 4 cubed equals 64, so 3 equals x minus 1. Since log 4 of 64 equals 3. And x equals 4. So our answer for the first question is going to be x equals 4. For the second question, we do the same thing. ln 15 equals 2x, right? So then we make it, because we just do using our log route. Sorry, I can't talk. Log laws, right? So it's just log base e to 15, except log base e is the same as ln e, natural log. So ln 15 equals 2x, so x equals ln 15 over 2. Now let's solve this question. We know by multiplying that, our addition law, or product law, sorry, that this equals x squared plus 6x. Log 3 of x squared plus 6x equals, and that equals 3. And 3, and now we just solve for it. So 3 cubed equals 27. So x cubed. So, and then becomes x squared plus 6x equals 27. We subtracted the 27, so it becomes x squared plus 6x minus 27. And this becomes, and we factor this out into x plus 9, x minus 3. All right. So our answers would be -9 and 3, but we know that our arguments can't be negative. So if we plug in -9, it does not work. It becomes negative. So our only answer is x equals 3. And our domain check is going to be our argument has to be at least greater than 0 because that's what our least thing is. Like if it was 0, then this side wouldn't work, and on this side would still work because it's 0 plus 6, but then we have to have the whole equation working, so x has to be greater than 0. Okay, 2.14, log context and data modeling. So this is, oh yeah, so this is like, there's a lot of real world applications to log skills, like in chemistry, for those of you that are going to be taking chemistry next year or are taking it right now, pH equals the pH of something equals the negative log of the H plus. And then there's pOH also equals negative log of OH minus. And there's a lot of applications for logs in mathematics, and they're commonly used. They were first invented so that to make it easier to do large multiplications and computations before they had like computers and calculators, right? So here, building a model when we use log regression or two known points, we do it in the form of a plus b ln x and or a log bx plus c. I have to interpret that each multiplication of x adds a constant to f of x. So here's a sound intensity graph. So vertical stretch is going to be 10. Sorry, does that say L? I think it says 1 over Li. Yeah, honestly, the quality on that isn't great. So I'm just going to skip over that one. Okay. So here's an example of like application of log. So if pH equals negative log of H plus and H plus equals 10 to the negative 4, then pH equals negative log of 10 to the negative 4. And 10 to the negative 4, log of 10 to the negative 4 is negative 4. And we multiply by the negative in the that's in front of it. So pH just equals 4. So how many more times more acidic is pH 3 than pH 5? So if you guys said like 5 over 3 or something, no, because it's actually in the form of like it's in the log form, right? So it would be log 10 and then like let's say like 10 cubed versus log 10 to the 5. So it's actually 100 times more acidic, not like 2 times. A sound measures 80 decibels. How intensive is it in relativity to, is that I of O? I'm not sure, but it's going to be 10 to the 8 times of I of O. So it's going to be like way larger than just 80 times. 10 to the 8, that's like over a million. If I'm not wrong. So these last two questions here. Find the pH when the H plus is 3.2 times 10 to the negative 6. An earthquake is, and then the earthquake is 1,000 times more intense. Reference I of O. Honestly, I don't think in pre-cal you guys won't be working too much with questions like this. So I'll just go ahead and like show you guys how to solve them. But it's good to know, so I'd still pay attention. So find the pH if, and remember the pH equals negative log of H plus. So the pH is going to be, if the H plus is 3.2 times 10 to the negative 6, then we can just uh make that. So it's going to be negative log 3.2, so 3.2 times 10 to the negative 6. So the pH for this would be 6 plus, no, 6 minus log 3.2. And acidic or basic, this is more like a chemistry question. I'm not even gonna like ask you guys this, but it would be acidic because it's below 7. I'm gonna skip over that one again. I think it's tested too much. And I'm gonna save semi-log plots for the next class since it's a pretty small topic and we can cover it. And I don't want to go over time right here. So there we go. We'll look at semi-log plots next time. And with that, we are done for today and we covered topics 2.11 to 2.14. So I will see you guys next time.